Hello, my name is Maximilian Grüner. Welcome to my talk on reconstructing proprietary video streaming algorithms. Let's get started. I want to start with a roadmap of what I'm going to talk about. We will first start with some motivation as to why adaptive video streaming algorithms, or in other words, ABRs, are an interesting target for reconstruction and what this paper aims to contribute to the community. Next, I will explain how we do reconstruction. After that, I'll show results from the metrics we evaluated. I'll then talk about the limits of our work and what we still envision. Finally, I'll close with some takeaways. So why are streaming algorithms relevant? First, we can look at the global share of internet traffic by application. When we plot traffic for different applications, one thing stands out. All of them pale in comparison to video streaming. Video streaming itself consists of a large variety of small players and a few really big ones like Netflix, YouTube, and Twitch. But there's substantial interest and investment from industry. But how does it look on the side of academia? As a proxy for academia, we can look at the number of Google Scholar citations over the years. We undoubtedly see huge growth in interest. This means there's interest from every side into these algorithms. But why are they an interesting target for reconstruction? First, ABRs are part of a big business which generates a lot of income. As they don't have a public-facing front end, one might copy these algorithms by simply interacting with the latter. You can obfuscate code, but it's not as easy to obfuscate behavior. It is crucial to understand the risk of competitors copying these algorithms. Second, there is a large investment from the side of academia into this area. Head-to-head comparison between newly proposed research ABRs and industrial ABRs has been lacking in the literature thus far. Through reconstruction, we can simplify this. Thirdly, given that the video is the majority of internet traffic, this traffic being controlled by an unknown proprietary algorithm implies that we do not understand the behavior of most internet traffic. If we were to be able to reconstruct parts of streaming logic, this could alleviate the problem significantly. All of these cases require not only functional equivalence, but also a certain degree of readability in order to ensure robustness, adaptability, and interpretability. For example, a competitor seeking to copy the ABR logic of an online service needs not only functional equivalence, but also interpretability to be able to reconstruct and to modify the reconstruction as necessary for their use if they do need to. We will need three parts in order to be able to reconstruct ABRs. We need learning, the data on which to learn, and a metric which tells us how well our behavior is fitting the reference data. First, we shall start with learning. For this, let us do a quick refresher on how ABRs work. Generally speaking, a video is separated into chunks of a given play length. Each chunk is played at a resolution, and when downloading the chunk, we can measure the throughput of the network, which informs us about the connection quality. If we still have space in the buffer, the algorithm requests the next chunk at a resolution related to the network quality. In this case, we just have a start of the video and notice that there's a lot of throughput available. This means in the next step, we're going to upgrade the quality. Then we'll notice that this was just a spike, and regulate the quality back down accordingly. This very simple ABR algorithm could be written down like this in code. The important loop of this algorithm takes as an input the measured throughput of the last chunk downloads, and then uses the most recent measurement as an indicator for the future network quality. If it predicts low throughput, we decrease the quality by 2 levels. If it doesn't, we do the inverse. We see a very prominent if-else structure here. This can easily be transformed into a decision tree. We can see that the core logic of the algorithm is reconstructed in this tree. As this is a well-researched technique, we have a tool in hand that supposedly can reconstruct ABRs in a succinct way. Though there's one problem. Unmodified decision tree learning only works in a simple case, and we see in the next slide why this is going to be a problem. Just taking a last throughput estimate as a reference value might prove unreliable, and one obvious improvement to our existing algorithm could include the usage of a mean of the last 2 measurements as a throughput estimator. This introduces the problems for the learning algorithm. In this graph, we see the decision boundary between the last and second to last throughput. If the mean is above a certain threshold, we upgrade the quality in green, otherwise we downgrade in red. Now we try to fit a decision tree on this. Remember, if-else rules can only represent horizontal and vertical lines in the decision space. With just 2 rules, one rule representing one path from the root node to the leaf, we obtain the obvious center separation. As we increase the number of rules, We become better and better at fitting the line. Though even with 100 rules, we're only able to fit this line approximately. Having these many rules also runs counter to our interpretability constraint. Therefore, in order to keep small trees expressive, we need to encode operations, such as the mean, as primitives. Given enough training data, the learning algorithm should choose the most fitting primitive itself. Throughput estimators, though, are not the only thing we want to encode into our model, as we shall see next. Deployed algorithms are likely to grow more complex than we can just model up until now. Take, for example, this. They might take into account the buffer of the player. The buffer acts as a chunk safety deposit from which we can draw. This means that we do not necessarily need to downgrade immediately when the throughput is bad. We can estimate whether keeping the high quality would incur rebuffering and then decide. This kind of logic again would create similar problems to one we experienced before, as we introduce a division when calculating the download time. Beyond throughput estimators, we therefore also need more complex logics into our primitives and add these. But how many primitives do we now use? The number of primitives are defined by the types of primitives, how many measurements in the past they consider, and how many actions we consider. In total, we include roughly 1,300 primitives. Building on primitives and decision tree learning, we conclude the first part of our learning procedure. Next, we need to define which providers we want to apply the methodology to. We start out by including the big global players such as YouTube and Twitch. After that, we also want to select small regional providers. Lastly, we obviously also want to select providers which are prominent in their content niche, such as pornographic video websites. All in all, we obtain data for these 10 providers. Unfortunately, we had to leave out many commercial players like Netflix, Hulu, and Amazon Prime, as the terms of service agreements are very narrow and don't allow for automated training generation. We test these multiple providers across multiple network traces sampled from different trace collections used in past work across multiple videos, and each provider with an experiment lasting several minutes of streaming. In total, we measure nearly 9 hours of video streaming for training and testing respectively. Finally, we need to tackle the last problem in our learning pipeline. How do we ascertain the quality of our learned tree? We have to use two kinds of metrics for this: general metrics and domain-specific metrics. If you want to show that selecting a general metric is not straightforward, with the next example. Let us go back to our first streaming example. An ABR decides the quality solely based on the last throughput estimate. We simplify the situation a little bit in the sense that the throughput is now high and stable. We, in this situation, apply our learning algorithm, this fixtures algorithm, and obtain the following behavior. It chooses the same quality in the beginning, but then only increases the quality by 1, and then by 1 again. Strictly speaking, we don't match any of the quality, any of the algorithm's decisions. This means in terms of agreement, we have failed. But for 2 out of 3 chunks, we display the same video quality, which on the other hand indicates that we have not done such a terrible job at actually reconstructing the behavior. The other side of the coin for agreement is where we mistakenly fetch a very high quality chunk instead of a low quality chunk. This incurs a lot of rebuffering and changes the video experience without changing the agreement overly much. This means only relying on matching the decisions alone will be too much of an imprecise metric. We therefore combine agreement with a similarity measure through a harmonic mean. In order to arrive at a metric for agreement, we can look at a simplified problem. We only have 2 qualities to select from. We have a, say, set of situations where the streaming algorithm has to decide whether to upgrade or downgrade the quality. And in part of them, we upgrade. We then choose a subset, or rather the algorithm chooses a subset of environments where it upgrades. Among these elements, we sometimes choose the right action, and sometimes we don't. From this, we can calculate 2 metrics: the precision, or how often was I right to select that action, and recall. How many of the actions should I have taken, have I taken? We combine these 2 metrics into the F1 score. The F1 score is constructed from the harmonic mean of precision and recall. We calculate the score for every decision separately and then take the mean. This is called the F1 macro score. We now move on to the similarity metric. In order to understand similarity, we make a small excursion into clustering. We can take each decision taken by the reference algorithm and the situation it was taken in, and embedded in a 2D space. Here we'll plot this as simple yellow points. Next, we can fit a function to this, which tells us where in the space the decision lies and how likely a point in this space makes part of said decision. We can assign new decisions to two classes now. Are you close enough to what I've seen, and have you been therefore taken by the reference? Or are you too different and therefore don't belong to this class of decisions and I have not been taken by the reference algorithm? We train our isolation forest to do this for us, to predict the probability of a decision taken by the imitation to be indiscernible from a decision taken by the real algorithm. On a side note, only optimizing for this is also counterproductive, as the algorithm which resembles the industry standard most is the one that always keeps the same quality. This is the case because industry algorithms tend to opt for a more stable tuning experience, as we have found in a paper published earlier this year. We compare the agreement and similarity achieved by our rule set approach against the best black box approach in a simple rate baseline. Why do we do this? We choose these as loose lower upper bound for our approach. If the approach is not better than a generic rate-based approach, it's most likely not very useful, and we can't expect it to be a lot better than a black box approach. The top right corner contains the best, and the lower corner contains the worst reconstruction. The black box approaches are comprised of two imitation learning techniques and one neural network classifier which tries to match the decision directly. The rate-based approach works very similarly to the example algorithm provided at the beginning of this talk. The rule set we consider can at most contain 20 rules. The number of rules is a hyperparameter which has to be tuned for every provider individually, while also taking interpretability into account. Our comparison over the 10 providers also includes NPC and Pensive, NN in this graph. Two academic approaches evaluated on the Twitch video. The first thing you see is that the rate-based approach achieves not only very low agreement, but also very poor similarity. The rule sets achieves nearly the same or better agreement than the black box approach. In the worst case, NN, the rule set agreement score is 8% lower. In many cases, we achieve higher agreements than even the black box approach. This is due to the imitation learning approach trying to achieve higher similarity in terms of behavior rather than matching each individual quality decision. It is important to note that an F1 score of 50% does not necessarily indicate a bad match, as I've already started explaining earlier, and what I will see again later as we look at these results in conjunction with the perceptual metric. With generally good matches in terms of the agnostic metric, I want to now show on 3 levels how these reconstructions can be useful. First, assessing the risk of reconstruction through a competitor. Comparing industry with academic approaches and using the interpretability to get insight into the decision process of the tree and then show how it can be used for development. First, let's look into risk assessment. For this, we need to attach user experience translation to the agnostic metric. A competitor wants to provide similar user experience to the leading one, after all. We choose as a stand-in for a modern visual metric the WIMF score developed by Netflix. The score ranges from 0 to 100 and compares the current quality of a chunk with the highest quality provided. The second dimension includes the change over time of said score. And lastly, we measure the impact of rebuffering. First, we plot the measured values of the provider with the hatched markers. We see most providers are centered around the middle with 2BTV and Pornhub straying a bit. Netflix adds next, we add the corresponding approximations. For 9 of 12 targets, we achieve a very good match. The mean WIMF for these 9 reconstructions is within 6% of the targets on average. YouTube and porn and Venom are sadly outlier. For these, we have large discrepancies. We further investigated these 3 results. We find that Pornhub often switches to progressive download, disabling video quality adaptation altogether. Our approach ends up overfitting on the progressive behavior as we see very few switches. Excluding the progressive download improves the reconstruction significantly. For fandom, we find that the issue is the limited complexity of our rule set. A rule set with a somewhat higher complexity performs substantially better. As mentioned before, the number of rules is a hyperparameter which needs tuning for different providers. YouTube, in addition to making quality decisions, varies its segment length and can also redound low quality chunks to replace them with high quality ones. YouTube is solving a different problem than we expected. This is a fundamental gap in efforts like ours. If the decision space is not appropriately encoded, outcomes will be suboptimal. We've resisted to use the benefit of hindsight for this work. We have ascertained that for most algorithms, we will obtain a visually very similar experience. This gives us more confidence in actually taking these algorithms and comparing them in a different testbed. We next want to look into how these reconstructions behave in an academic comparison under the same metric. To this end, we extend the DASH architecture with implementation of the rule set reconstruction for the 6 targets we were able to match most closely. The same setup has ground truth implementations for BOLA, Ankit, and Pensive. We evaluate them of QE using the in-vivo video typically used in academic work and normalize the results for the mean QE for Pensive. Pensive and MPC generally outperform the deployed ABRs reconstruction. This is perhaps not unsurprising. We are evaluating a providers with QE functions used in academic literature, while the provider may, in fact, be optimizing for a completely different goal. Most striking is the distribution-wide extremely close match between CTF and BOLA, except for a few other details for most video trace pairs. The performance is virtually identical. Thus, it is likely that CTF is using BOLA or a derivative of it. And lastly, we want to look how we can build even more trust in our reconstruction, and what kind of insights we gain when looking at the actual structure of a tree. The tree I'm showing is the simplified for a tree for SRF, which contains obvious flaws, which are not contained in the full tree, but help to highlight the benefits of interpretability. First, it checks the point in playback, concluding that it is in a startup phase if the playtime is below a certain threshold. In the startup phase, it checks if the possible gain and reward is large enough to warrant a leveling up by 2 levels. This is only done if you don't deplete the buffer by too much when doing so. Beyond that, depending on which phase we're in, we probe different quality levels and only upgrade the quality if the throughput is very good. We find an interesting characteristic of the simplified SRF tree in the post-startup phase. There are no quality changes. This is clearly unsuitable in practice and would be an obvious red flag to any domain expert examining this tree. The full tree does, in fact, use adaptation after startup too, although it is infrequent. We have verified this behavior experimentally as well, where SRF makes frequent quality switches during startup and much fewer later. With this toy example, we can see 2 benefits from having an interpretable tree. Before we even deploy the tree, we can check whether the behavior makes sense and whether changes have to be made manually. Second, for each decision, we can trace the input-output mappings and look for unsuitable behavior after deployment. We use this methodology intensively while developing our approach to verify and adapt different sets of primitives and training methodologies. I want to now move on to the limitations of this work and the future work we envision. Accurate and concise trees require intuitive primitives. For example, moving averages, which must be manually encoded. Perhaps such primitives can automatically be captured from a corpus of available hand-designed network algorithms, but this is likely a challenging task left to future work. We can only train for appropriately specified decision space, as is clear from the failure of our approach for YouTube. We can expand the decision space with the benefit of manually drawn observations from experiments, but automatically discovering them seems hard. We use an intuitive but subjective definition of interpretable. Trees with under 20 leaves and domain-specific literals. Our own experience of understanding was possible, but we hope feedback from other researchers will help sharpen interpretability goal for future work. For providers that customize their ABR for different regions and set of clients, we can only reconstruct the behavior we observe from our test clients. For future works, this opens an interesting opportunity. Observing differently tuned versions of the same ABR, it might be possible to achieve higher quality reconstructions, which also identify the parameters whose tuning varies across regions. As for the takeaways, decision trees are a great and versatile tool if you combine them with primitives that reflect our knowledge about the problem. Interpretability can help us catch problems before they occur or help us fix them after the fact. It also gives us a metric-independent way of verifying our results. On the limitation side, we don't have to recognize that interpretability is subjective and that the creation of readable and useful primitives takes a lot of time and domain knowledge. We also are limited by the fact that we can't model what we can't expect, or rather do not expect. Our approach therefore might fail for algorithms which include primitives that are unlike anything which has been deployed so far. With this, I would now like to conclude my talk and thank my collaborators, Licciardello and Ankit Singla, for all the hard work they put into this paper. I'm now open to questions, and you can find the code necessary to reproduce our results in this repo. Thank you very much.